I'm going to start with introduction of maximizing and minimizing value. Maximizing and minimizing area refer to finding the largest value, which is maximum, or smallest value, which is minimum, possible area of the given shape or region subject to certain constraint. In calculus, this is often achieved by creating the mathematical models of the problem and then use the optimization technique such as differentiation to identify a critical point where the maximum and minimum area occur. So we use maximizing and minimizing area in calculus because it helps solve real life problem. Involve optimization, where the goal is to make the best use of resources or achieve the most efficient outcome. These concepts are crucial in various fields such as engineering, architecture, economics, and physical, where the area is often the critical factor.
Next, we will go to the problem statement. The figure shows a piece of wire with the length 130 cm, which is bent into the shape A, B, C, D, E, F, G. Given that BC equal to DE, the first question is express x in the term of y. Second question is show that the area enclosed by the wire is A equal to 200y minus 12y squared. The last question is hence find the maximum area of the shape.
So, how do we solve the first question? It wants us to express x in the term of y. So from here, the question already gave us a figure and it basically gave us all the information of all the sides. So from here we simply add all the sides equals to the number given. And right here, they gave us the number 130. So the term that we will end up with is 130 equals to 4y plus x plus 5 plus 2y plus x plus 2y plus x and plus x plus 5. And from there, we simplify the term to the point that we get 130 equals to 8y plus 4x plus 10. We simplify it further by moving the 10 to the other side, which will give us 120 equals to 8y plus 4x. And from here, we want to move the 8y to the other side, so then it will be equals to x. So we will get 120 minus 8y equals to 4x. And from here, we have to move the 4 to the other side so that x doesn't have any constant. So if we do 120 divided by 4, we will finally get the final term, which is 30 minus 8y equals to x, which is the final answer we need. Moving on to the next question. It asks us to show that the area enclosed by the wire is A equals to 200y minus 2y squared. So from here, we will separate the two shapes, which is one is a rectangle and one is a square. And from here, we will use the formula area equals to length times width. And from here, we will be using area of rectangle plus with area of the square. So from here, we will get the term area equals to x plus 5 times with 4y, which is the rectangle area, plus the square area, which is x times with 2y. And from there, we will substitute the value of x we get from the previous question into the term. So from here, we will get 30 minus 2y plus 5 times with 4y. And then plus with 30 minus 2y times with 2y. From here, we can simplify the term until we get 35 minus 2y times with y plus 30 minus 2y times with 2y. From here, the term 4y can be multiplied into the bracket to its left, and the term 2y can be multiplied into the bracket to its left. So then we will get the other term, which is 140 minus 8y squared plus with 60y minus 4y squared. From there, we just simplify the term, and then we will finally get 200y minus with 12y squared, which is the same answer as the term the question asked for. So for the last question, it wants us to find the maximum area of the shape. From here, we will be using the original equation they gave, which is a equals to 200y minus 12y squared. We will be using two steps, which is by differentiating it the first time and then the second time. So from here, after differentiating it, we will get a prime equals to 200 minus 24y. We will then solve it equals to 0, which will get us y equals to 25 over 3. The second step, we have to differentiate that equation the second time, which will give us a prime prime equals to minus 24, which means the value is less than 0, that it is the maximum value. So from there, to find the a max value, we will be substituting the y we found into the original equation, which will give us a max equals to 200 in bracket 25 over 3 minus with 12 in bracket 25 over 3 square. We just simply solve it. That will give us the final answer of 2500 over 3 or 833.33 centimeter.
Maximizing and minimizing areas are crucial applications of calculus that focus on finding the largest or smallest possible area within specific constraints. These concepts are widely used in solving real-world optimization problems, such as designing structures with maximum efficiency, allocating resources effectively, or optimizing land usage. By applying techniques like differentiation and critical point analysis, we can determine the most efficient solutions to practical problems involving shapes, regions, or boundaries, making these mathematical tools invaluable in engineering, architecture, and various scientific fields.